Well, thank you to the organizers for organizing this. I think it's been a fantastic discussion so far. So I am fascinated by the fact that almost no matter what you do, if you continue to do it, you eventually get much better at it. Maybe not this good, but you do improve. I suspect many here are also interested in our learning capacities. And I think from a scientific perspective, we really do need to understand the learning capacities that humans and other animals have, because it could be a route towards a big compression of our knowledge about the brain and mind. So here's the principles of neuroscience. In 1981, it was 468 pages. 2012, it was 1,700 pages. If you're an experimentalist, this is amazing. Congratulations, it's excellent. But for theorists, you could argue, maybe we'd actually want this to be coming down if we were really finding succinct descriptions. Okay, so one remarkable convergence, which will surprise no one here, is that in the machine learning world, we're seeing a big convergence in methodology and methods. So the same systems that can recognize objects and images can also play Go and do a host of other activities besides. And those also have a shared history in neuroscience. And these are, of course, artificial neural network models that we're all familiar with. And so I think it's worth trying to understand exactly how much learning in the brain is like what we're doing in artificial intelligence. And to do that, we need to do lots of things as a field. But the approach that I'm going to lay out here is these sort of three categories of things. So first, we just might want to take these artificial networks on their own terms, study them mathematically, and try to understand some of the core behaviors that they have. And if you can get some insight into how they work, you could probably convert that into a theory of a particular domain. So maybe we're looking at vision, you add assumptions about the data that system is receiving, and you make specific predictions for an experimental domain. And then finally, we need to actually run these experiments and hopefully get a loop where we can start testing and empirically vetting these different principles. So what I'm going to talk about today is very brief vignettes from these areas, talk about dynamics of learning and some universality phenomena. That's the theory level. And then I'll show how those concepts that emerged there, we took and tried to build a theory of human semantic development, and also finally an experiment that we've recently been working on to test some of these predictions in mice learning a visual task. May not have time for all of this depending on questions and so forth, but we'll see how we go. Okay, so first let's talk about the theory side of things. So one thing we know from a lot of work in engineering disciplines is that when you make a system deep, it can complicate the learning dynamics. So here's a shallow network. It's just got input layer going to an output layer. And if I train this on some task, the task is not important here. You can see that the error just exponentially decreases. But if I really change nothing about the setup except I add these intervening processing stages to this network, train it on the same task, now you can see it's got these complex trajectory with these little stage-like transitions and plateaus where it's not doing much. So we'd like to understand something about why depth is giving this richer phenomenology. And this is a broader task that, I think for deep learning theory, basically as the designer, you pick the data, the architecture, the algorithm you're going to use. And we usually use computer simulation to sort of understand what's going to come out of this over a longer term period of training. And these are the quantities we really care about. How fast will it train? How is it going to generalize? What representations might it learn? And so the task for, at least one of the tasks for theory is to say, how do the choices over here eventually impact this without needing to run the simulation? And to do this in generality, of course, we can't, or at least I can't. So we're going to look at surrogate models. And this strategy might be familiar if you're coming from physics. We're going to look at simple toy problems to try to crystallize some of the phenomenology, way simpler than the real thing, but that nevertheless have some key features. So that means they're not going to work, right? But I think for brain sciences, it can be important to have the conceptual clarity that you get out of these models. All right, so the first model I want to talk about is called a deep linear neural network. So here's a sort of feed-forward nonlinear deep network, standard setting. The deep linear network is a drastic simplification we're going to just strip out all of the nonlinearities, okay? This will be our deep linear network. And we can train it, for instance, to minimize the squared loss. And I just want to highlight, you might be thinking, wait, this is surely trivial because you're just multiplying a bunch of linear maps, it's still a linear map. But it turns out that the nonlinearity comes back in when you're considering this loss function, right? This is nonlinear. And this minimization problem is non-convex once there's one or more of these weight matrices. This is a little toy model of a non-convex optimization problem. And these are the gradient dynamics. If you look at them for a sec, you'll see that they're just quite complicated, actually. They involve cubic interactions. And as you change the depth of the network, these gradient flow dynamics change as well. So our task is to understand what the solutions of this look like as we change the depth of the network. Now, this is still a bit complicated to get your head around. So I think the best I can do for boiling it down right now is this linear chain. So now we don't even have multiple hidden neurons. We've just got one neuron per layer in this chain, giving it a 1 as its input. It's trying to produce a 2 as its output. This is hopefully quite simple. And I'm further going to assume that all of the weights in this network are initialized to be the same value b, okay? And then they'll stay that way under training. And so we just have this one parameter, which is defining this network, which is the starting weight in all of these layers. And now this is simple enough that I can show you the real loss surface for this network as a function of depth. So on the x-axis, we have whatever the layer weight is. And on the y-axis, we have the error of that configuration. And the different colors here are the depths of the network. And what you can see is that for a shallow network, we just get this nice quadratic bowl. And that's going to proceed very well under gradient descent. You imagine dropping a ball on that surface, it will be just fine. But in the deeper networks, you see that there's actually this plateau that's forming. And it turns out that's because there's a saddle point at the origin of this lost landscape. You make no progress if the weights are exactly 0. And if you're nearby that saddle point, you're on this flat plateau region. So you can't really get stuck permanently, but you could be near that saddle point and you'll slow down near it. And so if I run the dynamics of a bunch of different networks that I initialize on this surface, you'll see that the shallow network learn very rapidly. And these deeper networks, they do learn, but it takes them a second to fall off this plateau and reach the global minimum in this setting. And the good news about this highly simplified setting is this is a case where we can exactly solve for these dynamics. So the exact form here isn't super important, but I'll just plot what the structure looks like. So in the shallow network, we see the weights essentially just exponentially increasing to whatever their final value is. And in the deep network, we see this qualitative switch, where now it's got a sigmoidal trajectory. So it spends a while near the saddle point and eventually expels from the saddle point to the correct solution. And the deeper networks, in the linear case, doesn't change things too much, it sort of changes the shape. But the qualitative lesson here is, what did depth introduce to this problem? Well, it transformed these learning trajectories from exponential approach into a sigmoidal, quasi-stage-like dynamic.
Here, the initialization was specific, right? All zeros. But that's not typical, right? We like random initialization and so on. So what carries over in that setting?
Yeah, so if you initialize them to be small random, then the picture looks very similar. If you initialize them to be large random, it's totally different, but you can still understand it from looking at this picture. It's sort of like you're starting over here. And if you look over here, actually everything's nice and quadratic, so learning's very fast here. There's no saddle point to get stuck on. That is true when you do large random weights. So there's a lot more to say about initialization, actually. It's a fascinating topic, but so far we're talking about the small initialization limit. Okay, so the good news is that that 1D chain that I showed you is all of the concepts you need to understand actually the full deep linear network, because with the right change of variables, the deep linear network in certain circumstances behaves just like several of these 1D chains that are totally independent. Okay, so you can think of its behavior as it's, instead of having just one of those sigmoidal transitions, now it might have several. But they don't talk to each other. So each one is just going to go through its sigmoidal transition, won't depend on the rest. And the overall network is going to result from the sum of these different sigmoidal transitions that are happening. And again, this property is preserved, where in the deep network you get stage-like transitions, whereas in the shallow network you can see they're all doing exponential approach at roughly the same time. Yeah.
So following up on Jitendra's question, if you go back one slide, I thought that you might get this multi-hop type behavior even with a single thread network when you initialize the weights differently. And so if you think that you initialize them with a Gaussian sampler, a few of them will end up near zero, and a few will end up far from zero. So what you would predict is that the ones in near zero stay put for a while. The ones that are far from zero compensate for it, so they become very large. But then since you have probably some L1 or L2 regularization on the weights, the big ones will pay a price and will want to become small. And in the meanwhile, the small ones have inched away from zero and have started collapsing down to the correct value. So you would probably see this multi-phase behavior in which there is a sequence of weights like here. You could see a multi-phase behavior just from this single file network.
So I should go away and think about that more carefully. I'm pretty sure, in fact, it only gives you a single drop still, even when they're not the same, at least without regularization, which is what I'm talking about here.
Yeah,
it could be very different. Yeah, then I think it could be different.
Then you should have a multi-phase.
The thing about this structure is, because you're multiplying, if any one weight drops the signal, it's gone. So
if it's exactly zero, but if it's epsilon, then something else would be 1 over epsilon.
Yeah, but my point is that the overall product is what matters. And so it really does seem to usually go through one transition, because it's not like some learning helps you very much.
Well, it's something you can test in a few minutes. We can bet at your end.
I can certainly tell you that if you just, maybe I should have said this. If you just initialize a deep linear network from small random weights, this is really randomized. The red here is simulations. You can see the predictions line up very nicely. Okay, thanks. So the qualitative picture emerging from this is that we have something like this. This is not a real loss surface, just trying to illustrate the idea. We have a hierarchy of saddle points in our deep linear network. And so if we drop trajectories on this landscape, they will go through a trajectory that has a combination of systematic structure, but also variability, right? Because a small change in where you initially start off, you could fall off different sides of these saddle points, and therefore see some individual variability as well. So I think this is one interesting prediction. And if you believe this version of things, then basically, if animals were learning a similar way, you should see a mixture of individual variability, but also systematicity, where they come and dwell near these strategies and then continue on through this picture. Okay. Now that was all for linear networks. No interesting task is linear. So I just want to sketch some of the ways we've been tackling nonlinear problems. And we've been motivated to try to understand rectified linear nonlinearities. And that's because they seem pretty close to linear. So if you think of rectified linear, either you're linear or you're off. And so what we can do, and I'll just sort of sketch this conceptually, is consider all of the paths through the network. On some given example, some of those paths will have neurons that are active along the whole path from input to output. Other of those paths might have somewhere along that chain an inactive neuron, and then that whole path just falls out of the operation for this particular example. And so using this, it turns out that under certain circumstances, you really can show that such a network like this will behave like a deep linear network for each pathway, where that pathway doesn't see the whole data set, it sees the subset of data for which it's on. And you're learning a bunch of these linear models that are mixed together on different examples to do, at that point, nonlinear computation, sort of like a linear model tree. So just to give some intuition for how this works on a simple problem, here's the XOR problem. We could try to solve it with a one-layer ReLU network. And what we're saying is you could look at this one neuron's weights here as a vector back into the input space. And at initialization, that vector might point in this direction. It might be very small if it's a small random weights, but it'll point in some direction. And because it's a ReLU neuron, it's going to be active in one half space and inactive in the other half space. And so from its perspective, the problem looks something like just dropping those data points where it was inactive on. And then you solve the linear problem corresponding to the remaining data points. Some other neuron in this network will point some other direction. This generates its own effective data set. You solve the linear dynamics for that data set. And when you do this process, you can then stitch things back together to get a prediction for the full dynamics. I'm sweeping lots of technical details under the hood. We know it's approximate, it's not exact, but it can be highly accurate. And so here is a network that's quite closely equivalent to a ReLU network on the XOR task. It just has different groups of neurons, 4 groups in the hidden layer, each of those groups active on 1 out of the 4 examples. And when you plot the predictions of this model over the dynamics of a real ReLU network, so this is a real ReLU network trained from small random weights, you can see that it predicts the trajectories reasonably well. So there are cases where we can extend this analysis to the nonlinear setting. All right, so just to summarize these first few points, shown that depth can introduce saddle points, dynamics slow near these saddle points, creating stage-like trajectories. And these saddle points are arranged hierarchically, and they yield a quasi-systematic progression through stages. So you learn the most important one first, essentially. I didn't really highlight that, but it's true. And then you go through the less important ones later. And in nonlinear networks, some aspects of this can generalize. You can think of different pathways going through this process, essentially, alongside each other. All right. Next, I want to talk a bit about some recent work trying to understand universality phenomena. So this is motivated by the striking finding that when you train a bunch of different architectures, here, different VGG nets, AlexNet, ResNets, and you look at the similarity of neural activity in different, to different images in a data set, you can often see a pretty similar qualitative structure, even in these different networks. And this is also true. This is a nice paper from Conwell and colleagues. So on the x-axis here is a whole bunch of different architectures, including transformers over here, convolutional networks here. And they're looking at how well these models can predict neural data. And you can see that, yeah, there's differences, but really a lot of them are doing very well. And in fact, the amount of variance they're explaining is comparable across convolutional networks and transformers. And so this neural predictivity can be similar even across very different models. So we want a simple model of when and why this might be the case. And what I want to suggest, okay, well, first of all, why would you be interested in these type of universality phenomena? Well, it's very efficient. If you can say something about it, you would then make a statement that applies to many models in this class. And I think equally importantly, it says that it's not crucial to focus on all aspects of the situation. There's probably some way of seeing this similarity that sort of frees you from considering all of the details. All right, so what's the approach? Well, I'm going to argue that one feature shared by many of the architectures we train is expressivity, right? We train these massive models. They're very complicated. And so aspects of common behavior could come from this fact that we're in the high expressivity regime. So let's think about that regime. And this is really the idea of my student, Luc van Rossum. I think it's a really cool idea. So he says, take this nonlinear network, whatever it is. If it's complex enough, then I can kind of think of it as just any arbitrary smooth map from my inputs to my hidden layer, and then another smooth map from my hidden layer to my output. It's not strictly true, obviously, but maybe it's approximately true. So we just think about it as any smooth map here. And hopefully you can see why this might be a unifying perspective, because now I've got some other architecture. Maybe it has a different activation function. Maybe it has a different number of layers here. Nevertheless, it's still so expressive that maybe we can think about it still as essentially an arbitrary smooth map into its hidden layer. So what can we do with this model? Well, we can consider what happens on a data set that contains just 2 data points. So this is our massive simplification. And we can ask, if I present these 2 data points, they'll have some representation in their hidden layer, and they'll map to some output. And I don't necessarily, and we're trying to get some desired target outputs. And I don't necessarily need to consider everything about them. I'll just ask, first, how do these hidden representations move closer or farther apart? So I might want to track just the distance between them in the hidden layer. Secondly, I might want to track how far apart are the predictions that the network is making in the output. And thirdly, I might want to know how those predictions are aligning with the correct target labels. All right. So those three summary variables, they don't tell you everything about the geometry, but it turns out that we can get a consistent system of differential equations that describe how these change. And I won't go through the details. I will just say that nothing about this is mathematically correct. It is actually all phenomenological, but it appears to give good predictions. So yeah, the details here are, let's just say, shaky. All right, so what comes out of it? Here is an example of these three quantities as we're training a 20-layer ReLU network with 500 units per layer. So a leaky ReLU network on these two data points. And if I overlay the outcome of the theory, you can see it can describe the changes, the coordinated changes in these variables pretty well. One comment here is there are some free parameters you have to fit. So this is not a parameter-free prediction. But we've done a lot of controls on that. And we think it really is capturing a lot about how these models behave. Yes?
So imagine you keep the data the same in both simulation. And when students train their networks, they're advised to train them 2 or 3 times with different initial conditions for the weights. And we see empirically that this may cause very different outcomes in the learning process. And this is not represented here, so I'm wondering what is the trick to make them do the same thing?
If you want reliable results, start with small weights. The price you will pay is it will take forever to train. So you probably won't in the end want to do it. But if you have a large network with small weights, it will be very reliable. One thing I skated over is that the initial representational there's the initial conditions here. When you initialize with your random network, there's going to be some distance between those starting representations, and these dynamics depend on that. And so if you are in a regime where your initialization and your network size is causing the distance between initial hidden representations to vary a lot, then the dynamics can be very different. If the distances are quite consistent, then at least the prediction of this model and this follow trees that they will be very similar. Okay. So that was for this 20-layer ReLU network. We tried it for a range of different model configurations, and you can see it's not perfect, but I do think it captures some qualitative features that are shared across many of these models. Again, on this very simplified 2 example data sets, we thought it might break in shallow or narrow networks, but even seems to be reasonably accurate across a range of them. And I just want to close this section with the intuition for what this model is doing, because it's actually quite simple. It's all because of the assumption of a smooth map, not an arbitrary map. And what that's saying is that because of that smoothness and continuity, if these 2 data points are meant to have the same label, the same output y, then one way I can achieve that is by moving the input-output map at this, the hidden to output map to be closer towards the label of the second item. But by smoothness, the other thing I can do is move that representation closer to the other item. And it will have to be merging the labels for the output for those 2 items. And so that is a merging effect. 2 items that are nearby in representational space with the same label will tend to merge. Conversely, if you have 2 items that happen to map to basically the same point, there's no way to split them apart. You have to move them apart a little bit before the network can make the correct hidden output prediction. And so that's a effect that pulls them apart. So that's sort of the essence of the idea here. And I will just say, again, this is a model that can make predictions for nonlinear tasks. So here is it showing the predictions of this model for a range of different weight variance initializations. And you can see that it's capturing a lot of what we see in this case, a 20-layer, 500 units per layer. Okay, great. Maybe we won't talk about experiments. We'll see. Okay, so just to summarize this this perspective on these nonlinear models, I guess what I'm saying is, what will theory of deep learning look like? Well, at least one thing it can look like is there's this giant space of deep network systems that we want to understand with this zoo of items that are out there. And maybe one way to make progress here is to say, instead of trying to find some grand theory of everything, we just start looking at little restricted spots and not covering everything, but with enough of these, maybe you can start interpolating and get good intuitions throughout the space. Okay, so I think I'm going to skip the semantic development example, and I'll move on just very briefly to the experiment that we've recently run. And this experiment is trying to test the idea that if animals learned in a way that's similar to these networks, we should expect to see them go through a sequence of saddle points, and we should expect a mixture of individual variability and shared structure. And so we trained mice here to basically report whether a stimulus showed up on the left or the right of a screen. This is a very simple task. They're holding onto a little steering wheel, and they just flip it left or right, and they get rewarded if they get the action correct. And so we train these animals over 30 days, and we can see that they get better over time. All right, these are psychometric curves down here. It's not super important, but they do get better. But what was really striking to us is there is a lot of variability in their strategy. And so in the top row here, I'm showing you a mouse. This is its probability of picking right as a function of how brightly we present the stimulus. Okay, so that's the contrast. And you can see that initially this mouse is rightward biased. So it's just responding right regardless of the stimulus. Like day 7, always right? And then later on, that bias actually flips. So now at a zero contrast trial, which is just a blank screen, initially it was responding right, and now it's responding left. And then it's getting these two correct. And so now it's sensitive to the stimulus. But it's essentially, one way of describing this in words is it's detecting the stimulus on the right. And if it doesn't see it, it spins the wheel left. It's not really looking for anything on the left-hand side. And we see a lot of animals with this reverse pattern as well, initially responding left, and then a systematic change where we see that bias at zero contrast flip to the other side. So these guys are just looking for the item on the left. And then we see some balanced animals. So those were example mice, but we can quantify this in this plot here. And I think this one is the one to really focus on. What you're seeing here on the y-axis is the bias of the animals. And on the x-axis is how much they're paying attention to the right stimulus versus the left stimulus. And what you can see is that some of the animals sort of go up and then down to the right. Other animals go down and then up to the left. These are these two groups of animals. And there's a systematic structure over 30 days here where the initial side of their bias subsequently predicts which side they'll pay attention to of the stimulus when they finally do have this stimulus association. Okay, so how can we model this? Well, we can use a deep linear network, and I won't go through the details here, but I will say that when you look into this, okay, so first of all, when you simulate this model, only the deep models exhibit this interesting structure where they initially become biased and then later on pick up on a sensitivity to a particular side. And we can, for this model, calculate its actual saddle point structure and arrive at this graph, which we think sort of summarizes these results. Because it turns out in the deep model, this is the graph of saddle points, and it corresponds exactly to the strategies that we see. So here they initially know nothing. In this branch, they're getting right biased, and then eventually they're getting selective to the stimulus on the right-hand side. In this branch, if they fall off this way, they get left biased and eventually get selective to the stimulus on the left-hand side. And there's a third pathway where they kind of stay balanced the whole time. So we think this is some preliminary evidence that maybe something like this is consistent with the sort of learning mechanisms that these AI systems might have. I just want to say things could have been different, right? So another hypothesis a lot of people believed could be correct would be that the animals are hopping around. It's not these connected trajectories. maybe they're doing hypothesis testing, right? And then you might see them really hopping between these strategies. But that's really not what we see. We see a very connected strategy where they're on these trajectories. It's exactly what you get out of gradient descent, where it can only move locally. All right, so I think I'm out of time, so let me just wrap up here. So just to conclude, I think I've shown some features that depth can bring. I've shown, hopefully, that I think we can make some progress in understanding these systems by looking at simple models, and in particular, simplicity often requires finding the right concepts, so that once you've mastered those concepts, things are intuitive to humans. And I hope that that's a path towards a better understanding of these systems. Yeah, thank you.
So should we infer from these results that the gradient descent is happening in the mice?
No, no. I think all I would say at the moment is like, well, it's certainly consistent, because I mean that's what the model is. It's consistent, but it's probably just saying it's something perhaps a little closer to gradient descent than to hypothesis testing, for instance, your fast switching kind of story. But exactly how much it's constrained the picture is not clear. I mean, it does rule out other things. It can't be natural gradient, for instance. If mouse were doing natural gradient, it would just go right by these saddle points, no problem. So, yeah, I think it's not nothing, but it's maybe a little bit.
Yeah, I mean, it's the absence of negative evidence. You haven't falsified that as a hypothesis for learning the brain with this data.
Yeah, it's a question of like how many other likely alternatives remain consistent with.
Yes, that's the question. Right.
So if I understood the representational convergence part, it sounds like you're saying that if two nets are trained on the same task, then by smoothness, they will learn similar representations. Does this theory say anything about two nets trained on different tasks?
No, which is a great question. It doesn't in its present form. I mean, it would tell you what would happen. If those two tasks were kind of just some rotation of each other, I guess, then up to rotation, it would say they would then something similar. But it doesn't have this idea that even very different tasks would have to learn the same latents. Yeah.
Thanks for the talk. I have another question to the mouse data. So you have shown that mice switched the strategy in a session a couple of times from being left bias to right bias, from repeating choices to alternating choices. So here in the psychometric functions, it seems that you computed average psychometric functions across a whole session or a bunch of sessions. So did you ever try to look for different, within the session, different decision-making strategies or modes in these mice?
Yeah, it's a great point. So we are always averaging at over some number of trials. So it could be that they're doing fast switching, but on average, it's looking like this gradient process. That's certainly possible. The only thing I can say is, so Peter Dayan has a model that's looked exactly at that. And that model could have seen fast switching, but on a very similar task, he actually doesn't really see it there. So he sees an engaged state and an unengaged state. He sees the same progression through strategies that we see, but he doesn't see big switching between these left and right-handed strategies. So empirically, it doesn't seem to happen.
Let's take one more question, and Thomas, if you can get set up.
I really like this comparison between network data and mouse data, but it seems to me that there is one big difference, which is that the networks they expect IID data, whereas in the real world, IID data basically never happens. Are you trying to account for this? Is there any way to deal with that? I think it's maybe connected with the previous question also, right? That there are these temporal effects.
Yeah. So I mean, here we can present them with IID data, but it's definitely the case that animals seem to have an advantage on non-IID data. So continual learning, for instance, really hard for. So we do have other projects starting to look at that, both behaviorally and in theory, and that's a place where gradient descent looks really bad. And so it's probably not what the animals are doing, but that's nothing concrete. We do have the theory side of that worked out. So you can get exact solutions to continual learning and deep linear networks, understand more about how richer initializations change subsequent learning. That we have worked out, but we haven't done the experiments.
Okay.